Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lessons, we talked about the harmonics that are present at a pipe that is open at one end, or you can say closed at one end here. And of course, we said the fundamental frequency for that, of course, is going to be Fn or F1, basically fundamental equals to n times V over 4 times the length. Remember this. Okay, so let me write the equation just to remind you one more time. And of course, after that, let's say, then after that, of course, we did solve some questions in that regard. And of course, we did some comparison between a pipe that is closed at one end and a pipe that is open at both ends, of course. So you do remember that for a pipe that is closed at one end, of course, the fundamental is present, or you can say the fundamental frequency is basically equal to F, or F1 equals to N times V over 4 times the length. This would be the difference between closed at one end, or let's say both ends are open. If it is both ends open, instead of 4L, you're just going to write 2L here. And of course, in terms of the number of harmonics, of course, if it is closed at one end, there will be only the odd harmonics will be present. But if it is open at both ends, we will have both, let's say, odd and even harmonics that are present there. So this is basically the main equation. If it is, let's say, if it is the fundamental, this end is going to be 1, so 1 times this. We said the number of harmonics, or the harmonics that are present, are going to be the odd harmonics only, which is basically 1, 1, 3, 5, 7, and let's say on all that, yeah? So remember this, for a pipe that is open at one end, we have the first harmonic, the third harmonic, the fifth harmonic, and of course it follows that, only the odd harmonics, remember, yeah? But in terms of naming these harmonics, it could be a little bit confusing, so it's very important to know how it is, yeah? So now, in terms of this, now the harmonic that comes after this one is going to be the third harmonic, but sometimes in terms of naming, of course, you can call this one the first harmonic, and call the one that comes after, we can call it the second harmonic. But the second harmonic in a pipe that is closed at one end, remember, it is going to be the third harmonic. Or you can say, if this is the fundamental, the one that comes after, you can call it the first overtone, second overtone, and of course it goes on like that. So, and of course we covered all that. We ended up at this point here. That was the last question we've solved, of course, why a pipe closed at one end have different harmonics series than one, let's say, an open pipe. And of course, because we said because the open end becomes an antinode, and of course, while if it is closed, it becomes an odd. All right, and of course we have this study tip, which is also important because following this, we have a question related to this. As in vibrating strings or a pipe that is open at both ends, remember this, the difference between two consecutives. When we say two consecutives, that means, let's say, one harmonic, and then the harmonic that comes right after that, don't forget, okay? It is equal to the fundamental frequency, all right? So we can say, let's say, I'll show you, of course, the demonstration, how it is or what it is, but before that, remember this, if it is a string or a pipe that is open at both ends, the difference between two consecutive harmonic, it will be equal to the fundamental frequency. But if it is a pipe that is open at one end, the difference between two consecutive frequencies is going to be twice the fundamental frequency. So let me show you what do we mean by this one here. So let's say we have a pipe that is open at both ends, or a string as well. Let's say we have, or the difference, let's say, between, let's say, the fourth harmonics, okay? Let's say the fourth harmonic, and of course, let's say the fifth as well. Let's go back to this. So we have the fourth harmonic, let's say, and of course the fifth one as well. So we're going to find the difference between the two, yeah? So in this regard, we can say the difference in the fundamental, of course, we have F5, let's say. So the fifth harmonic, we can say, and of course minus the fourth harmonic, yes? So, but the fifth harmonic equals to what? Equals to 5 times the fundamental what? The fundamental frequency, you can say. All right, that is for this one, yeah? Minus, of course, the fourth harmonic is going to be 4 times the fundamental frequency, or fundamental, of course, fundamental frequency as well. Now, these two are common, of course, so now we can say 5 minus 4 times the fundamental frequency, because this is common, so we can take a common factor. So 5 minus 4, that is obviously 1 times the fundamental frequency. Remember, this is for both, all right? For both what? For a string, all right? And also could be for a pipe that is open at both ends, yeah? Open at what? open at both ends here. Both ends, okay. What if it is a pipe that is open at one end here? What would be the difference between two consecutive harmonics, okay? Remember this. So let's say we have one of the harmonics that we have, it is the third harmonic, let's say. When we say the third harmonic, of course, that is basically F3 here, but remember, we're not ordering the name, yeah? That also can be called the second in order, like the one that comes after the first one here, because we don't have the second harmonic here, so we have the third one here. So let's say we want to find the difference between F3 and, of course, F. The one that comes after F3, is it F4? No. Remember, this is a pipe that is open at one end, or you can say close at one end, that is the same thing, yeah? Open at one end. Open at one end, you can say, or you can say closed at one end, that is also fine here. So, and then the one that comes after F3, of course, that is F5 here. So if you're willing to find the difference between these two, these are called consecutive harmonics because they come right after one another, okay? Because there's no in between in a pipe that is closed at one end here. So we can say the difference in harmonics here, of course, is basically it becomes F5 or the fifth harmonic minus or F5, let's say, minus F3 here. So in this case, of course, but F5 equals to 5 times the fundamental frequency, and then minus third harmonic is basically 3 times the fundamental frequency here. So we can say F1 here. So once again, F1, or the fundamental frequency, take as a common factor. So 5 minus 3 times the fundamental frequency here, and of course 5 minus 3, that is 2 times the fundamental frequency here. So you can see the difference here, okay, between a pipe that is closed at one end and, of course, a pipe that is open at both ends, or a string as well. So because these two would be the same in terms of their fundamental or their harmonics here. So take a look here, right? Here equals to 1 times the fundamental frequency. That is basically the difference between two consecutive harmonics here. But the difference between two consecutive harmonics at a pipe that is closed at one end or open at one end, you can say, it is equal to 2 times the fundamental frequency here. Okay, so now basically this study tips, it tells you what I have just told you here. Okay, so now we have question 26. It says what? It says, a student records the first 10 harmonics of a pipe. Is it possible to determine whether the pipe is open or closed by comparing what? By comparing the difference in frequencies between the adjacent harmonics here. Okay, so can we just tell by the difference between their adjacent harmonics whether these harmonics belong to a pipe or a string that, or let's say a pipe that is open at both ends, or a pipe that is closed at one end? Remember, we have 10 harmonics. So how will it be possible to do that? The answer is yes. Just like we have said earlier, if the difference between two consecutive harmonics of these 10 harmonics, let's say, when you take two, let's say the difference between two consecutive harmonics could be any two. Could be between the first and the second. Could be between the fifth and the sixth, let's say, for example. Could be between the seventh and the eighth, let's say, or whatever it is. As long as you're finding the difference between any two consecutive harmonics, let's say, if the difference between the two consecutive harmonics is equal to the fundamental frequency, that means this pipe that has been used, of course, it has to be open at both ends. But once you find the difference between the two harmonics, if it equal to 2 times the fundamental frequency, then that means that pipe, or the pipe that is being used, is closed at one end. And of course, that is the answer to that. Okay, now take a look at this one here. It says, we've solved questions like this, but let's do this one as well, all right? It says, what is the fundamental frequency of a 0.2 meter long organ pipe that is closed at one end? So we have a pipe that is closed at one end. We have a length, okay? And then what is the question? It says, what is the fundamental frequency when the speed of sound in air is basically, or in the pipe, let's say it is 352 meters per second. So now this is pretty simple, or easy as well. All you need to do, remember, you have to know the equation for the fundamental frequency for a pipe that is closed at one end here. So what was the equation there? So we can say the equation for a pipe, or fundamental frequency for a pipe that is closed at one end, we can say F1 equals to N times V, that is speed of air, let's say, inside the pipe or in the pipe, divided by what? Divided by 4 times the length. Remember, if it was open at both ends, we would have used 2 times the length, but because it is close at one end, you can see here. Okay, so of course it's going to be equal to 4L. So here, remember, the fundamental frequency, so n equals to 1 times, what is the speed of sound in air or in the pipe? It is basically 352 meter per second, and then divided by 2 times, what is the length? The length is basically 2 or 20 meter. So you do the math, of course, fundamental frequency in this case equals to 440 hertz. That is the fundamental frequency for that pipe here. Okay, now we have another question. Says what? A flute is essentially a pipe open at both ends. So flutes are considered a pipe that is open at both ends, okay? The length of the flute is approximately 66 centimeter, okay? What are the first 3 harmonics of the flute when all the keys are closed, making the vibrating air column approximately equal to the length of the flute? The speed of the air, it is 340 meter per second. So these are, again, the application of the law, but remember, this time we have a pipe that is open at both ends. That is what the flute is considered to be. Okay, so once you find the first or the fundamental frequency, it says what? It says the first 3 harmonics, okay? So if that is the case, let's solve this one as well. So let's zoom out this a little bit. Okay, so let's do this one. Remember, what is the equation for a pipe that is open at both ends? Okay, so F, we can say F fundamental equal to N times V over 2 times the length. Why 2 times the length? Because it is open at both ends here. So once you find the fundamental frequency, of course, then of course we will find the 3 or let's say 3 harmonics. Yeah. So this would be 1. This would be second. Of course, we can find the 3rd harmonic as well. Remember, for a pipe that is open at both ends, we have all the harmonic series, both the even and the odd ones as well. So we have the first, we have the second, and the third as well. Yeah. So we can say for the second one, we'll say 2 times the fundamental. For the third one, we'll say 3 times the fundamental. Yes. So let's find the fundamental. Then we can plug in the numbers. Then it would be very easy to find this one here. So the fundamental n is 1. The speed of sound in air is basically 340. And then divided by 2 times the length. Don't forget to convert the length from centimeter to meter, because we're given 66 centimeter. So if you convert this one to meter, divide by 100, then of course you will get 0.66 meter. That is basically the length. So once you do the math, you will get 260 hertz. That is the fundamental frequency. Okay. Now once you find this one here, so all you have to do for the second harmonic, you just multiply 2 times the fundamental. For the third one, 3 times this. So we'll say 2 times 260, and this one 3 times 260. And of course, you will do the math. You will find the answer for both, which is basically going to equal to 520 hertz for this one. And of course, for the other one is going to be 780 hertz. So these are the 3 harmonics, let's say, for this flute, okay? And of course, having this length. Okay, that was for this one too. Okay, moving on to the next question. It says, a violin is a string here. So remember, whenever the instrument has a string, so that is very easy. Remember, whenever sometimes they don't tell you whether it is a pipe that is open at one end, whether it is a pipe that is, let's say, closed at one end, or whether the instrument has a string as well. So you have to know that, or at least know some of the devices, let's say, not the device, the instruments here. But whenever they tell you a string, just always remember that for string we only have, let's say, one, or you can say we have all the harmonics, and then the equation for the string is very obvious. The fundamental equals to n times v over 2 times the length. Okay, so we have a string. The length is 50 centimeter. Don't forget to convert this one to meter. Has a fundamental frequency of this much. What is the speed of the wave on this string? So basically, find the speed of the wave, let's say, on the string here. So remember this, when we have this speed on the equation, basically it tells you that this is the speed of the wave on the equation, not the speed of the air, let's say, on a string, let's say. So it's a little bit different there. But in terms of the equations, nothing changed. So we have the fundamental frequency, which is 440 hertz. Okay, and then we have the length of the string, which is basically 50 centimeter, that is basically 0.5 meter if you divide it by 100. And then the question is, find the speed, okay, on the speed of the wave on the string here. So once again, because we have the fundamental, we'll go with the fundamental equation. So fundamental frequency equals to n times v over 2 times the length here. Don't forget, we want to find the speed here, but this n is basically, because it is the fundamental, it is equal to 1. You can cross multiply the equation, so v equals to what? Or you can say v equals to, you can use cross multiplication, equals to 2 times the fundamental times the length of the string here. So 2 times, what is the fundamental frequency? That is 440 hertz, okay, and then multiplied by the length of the string, which is basically, the length is basically 50 centimeter, and that is 0.5 meter. So once you do this one here, 0.5 times 2, that is 1. 1 times this, so equals to 440. That is because it is speed, so it is going to be meter per second, and that is the speed of the wave on the string here. Okay. Moving on to the next question. This question is a little bit interesting, and I'll tell you why. Because it could be this question can be solved in multiple ways. Let's say that's one thing, and of course they can change this question in multiple ways so that they can change the thing that they require. For example, I'll tell you more once we go through this. It says a flute is similar to what? To a pipe that is open at both ends. So we have a flute that is, consider this to be a pipe that is open at both ends, and then there is a clarinet which is similar to a pipe that is closed at one end here. The question says, explain why the fundamental frequency of the flute is twice that of the clarinet, even though the length of these two instruments is approximately the same length, okay? So even though they have the same length, but of course the fundamental frequency of the flute is going to be twice of that of the clarinet. What is the reason, or what causes the reason? So stay with us and let's do this or solve this question together. So now let's do it the first way. There's one way we can do that, yes? So let's say, because a flute is an organ that is considered, let's say, as a pipe that is open at both ends, so we'll say, do you remember what is the wavelength for that? So the wavelength, let's say for a flute, let's write F for the flute here. So equals to what? Equals to basically half a what? Sorry, my bad, okay? So equals to 2 times the length here, okay? That is for what? That is for the flute. But for the clarinet here, okay, so I'll use lambda c, that is representing, we're standing for clarinet here, equals to what? For a clarinet, that is a pipe that is closed at one end, the wavelength equal to 4 times the length here. Okay, so if you compare the two here, can I say this is basically 2L, this is 4L. So can I say the wavelength of the flute is basically half of what? Half of the wavelength of the clarinet. Can I say this? Okay, if you are following, and of course if you understand this, that means basically understood half of the concept here. So you can see here, this is the wavelength of the flute is basically 2L, but the wavelength of the clarinet is 4 times the length. So I can say this wavelength is half of this one here. So the wavelength of the flute is basically half of that clarinet. But you do know that in terms of what is the relationship between frequency and wavelength? You do know that frequency is inversely with what? With the wavelength here. So if the wavelength, let's say, so basically if the wavelength, let's say, is half, then the frequency must be twice, yeah? So in this case, we can say the wavelength, or the frequency, basically, we can say the frequency of the flute in this case, okay, because it is half of that wavelength, so that means the frequency will be twice of that of what? Of the clarinet here, you can say, the frequency of the clarinet. So once again, okay, we do know that this is half of this. If that is the case, then the frequency, because frequency is inversely proportional to what? To the wavelength. So if the wavelength is half, then of course the frequency must be twice of that. That is one way to do that. And of course that is the answer. You can see here the wavelength of the frequency of the flute is twice of that of the frequency of the flute. That is one way to solve this. Yeah, there is another way. Yes? What is the other way? So there is another way. The other way is basically we have the frequency of the flute basically divided by the frequency of the clarinet. And we're talking about the fundamental frequency. Okay, so take a look. Now, all you need to do is write their fundamental frequency equation, and of course, you'll be able to find this equation that we've just determined or found here. So basically here, we can say the fundamental frequency for the flute is basically n times v over 2 times the length here. And for the clarinet, you can say n times the speed, you can say, divided by 4 times the length here. Don't forget. Now, because we can cancel some of the terms here, okay? Because that is the fundamental frequency, so this is 1, we'll cancel out with this one. Their speed are the same, basically, that is the speed of let's say the speed of the sound in the pipe, you can say, the speed of the air, you can say, the speed of sound, basically. And of course, because they have the same length, so these will all cancel with one another out. So what is left now here? So we can say the fundamental frequency for the flute, okay? Let me write F capital for the flute so that you can differentiate between the two here. So let's go back one step. Okay, fundamental frequency for the flute, and then over the fundamental frequency for the clarinet. Now take a look what is left in the equation. Here we have 1 over 2, you can say, 1 over 2, and then of course below the fraction or the denominator we have 1 over 4. Now of course if you do some math here, now this 2 of course is going to be what? Of course this one goes down, this one goes up, or you can say it becomes frequency of the flute, the fundamental frequency for the flute over the fundamental frequency for the clarinet, in this case, it becomes what? It becomes 4 over 2 here, you can say. Correct? That is this. Now you can simplify this, of course. This is going to be 2, okay, divided by this. And then now we can say, you use cross multiplication now. That is, of course, you can say 1 left here. So frequency of the flute here equals to 2 times the frequency of the clarinet as well. And of course, this is the same as what we have found in the first case here. So these are fundamental, don't forget. Okay, so of course, you can add 1 here, or you can just go with this. So you're free to choose whether you choose this one or the other one. These are both the same way, or you can say different ways, but it gets to the same conclusion here, of course. Okay, now we have another question, that is question 28. It says what? It says, the fundamental frequency of any note produced by a flute will vary slightly with the temperature change in the air. For any given note, will an increase in the temperature produce a slightly higher fundamental or slightly lower fundamental? So the question basically gives you a hint here. So when we increase the temperature, the velocity or the speed is going to increase. Let's say, of course, it says the velocity is going to change, but is this change is going to increase or decrease? And that is what you need to know. Now, normally, when the temperature increases, what do you think will happen to the motion of the air particles? Okay, because the temperature increases, so the kinetic energy of the air particle also increases, or you can say the air particles start to vibrate or move around faster. If they are moving around faster, of course, that means the frequency will be higher. Or you can say, or you can use the equation of this to answer the question, of course, yes? So we can say temperature is directly proportional, let's say, with the speed in this case. Or we can say when the temperature increases, the speed of the particles increases as well. Okay, that is one way. Even though the relationship might be not directly, but of course these two are related. Maybe there is a square root between the two, whatever. But what we know that by increasing the temperature, the speed of the particle increases. That is one thing for sure. Okay, the next thing we can say is this. The fundamental frequency equals to what? Equals to n times, let's say, speed or speed of the, let me write this one a bit nicer. So speed over, and it says, of any note produced by a flute. Remember, we said flute is a pipe that is open at both ends, so we can say 2 times the length, yeah? In another way, you can see that there is a direct relationship between the two. So we can say frequency is, or the fundamental frequency is directly proportional with the speed in here. By increasing the temperature, the particles move faster, so the speed increases. If the speed of the particle increases, or the speed of sound increases, that means the fundamental frequency will also increase for the flute here. So when the temperature increases, the speed of the sound in air increases because F1 is directly proportional to V, so the fundamental frequency will also increase. And of course, we have a note, don't forget, it says if the temperature increases, both the speed and the fundamental frequency increase. Okay. Now, take a look at this question here. It says, a human ear canal is about 2.8 centimeter long. Now, remember, when it talks about human ear, you have to think about what exactly looks like. Basically, there is a side that is open, and the other end is basically the ear canal that is basically goes to the eardrum. So eardrum is the boundary or the other side of the ear that is closed. So here's the question. Can we, or is the human ear like a pipe, or is it considered to be like a pipe that is closed at one end or a pipe that is open at both ends? And of course, you know the answer. Human ear is considered a pipe that is open, or you can say that is closed at one end. If that is the case, then we're going to use the equations for the human ear that are for the pipe that is closed at one end. If you know this one, of course, then the rest will be easy. Okay, so it says can be regarded as a tube that is open at one end. So the question like itself tells you that it is a pipe that is closed at one end, but what if they didn't tell you? Then of course you need to know on your own here. So what is the frequency around which we would expect hearing to be best when the speed of sound is 340 meters per second, and find the fundamental frequency of the ear canal. That is also easy. Okay, so let's make this quick here because we have the length, but don't forget to convert the length into meter, and we have the speed. So can you find the fundamental frequency? Yes, but the fundamental frequency for a pipe that is closed at one end here. So fundamental frequency equals to m times v over 2 or 4 times the length here. So the fundamental, that is 1. Let me write it here. So the number of harmonics that is fundamental, so speed is basically given that is 340, and then divided by 4 times the length. What is the length? 2.8 centimeter, but can I use centimeter? No. So it's going to be 0.028 meter. By using this, of course, now you can do the math, and of course the answer that you will get is going to be 3035 hertz. So this is the fundamental frequency, or you can say the hearing will be best when the frequency is around this much hertz. Okay, so guys, we'll end this session for now. Okay, next time, inshallah, we'll continue from question 32, and of course we'll solve what is left from this unit. All right, till then, keep practicing, and I'll see you next time. Assalamu alaikum wa rahmatullahi wa barakatuh.